My name is Prakash Murali, and today I'll talk about how to mitigate crosstalk noise in quantum computers using software techniques. Quantum computers are composed of a set of quantum bits called qubits, and the operations that we can do on these qubits are called gates. Currently, the quantum systems that we can build are small in size. They have 5 to 72 qubits, and the gates that we can apply on these qubits are error prone. So we call these systems NISQ. NISQ stands for Noisy Intermediate Scale Quantum. But in spite of the limitations of NISQ systems, these systems are capable of very powerful computations. So as an example, Google recently demonstrated quantum supremacy on a 54-qubit superconducting chip. However, large quantum applications like Shor's factoring algorithm require much higher resources than current hardware capabilities. So we need new architecture, compilers, and software tools to really harness the compute capability of these NISQ systems. So before we get into crosstalk and what it means, I'll give a brief background on noise in NISQ systems. So here we show the layout of qubits in IBM's 20-qubit Bob-Linggen system. The qubits here are the circles, and the edges show 2-qubit operations that we can perform in this system. For example, I can execute a controlled NOT gate, a C0 gate, on qubits 1 and 2. Now, because of difficulties in qubit manufacturing, qubit control, and gate implementation, these gates are imprecise. So for instance, this gate here has an error rate of about 1 to 2% per invocation. And this is the error rate when there's no other operation executing on this chip. Now, if I run, let's say C0 6, 7 also in parallel with this gate, then the error rate is actually much worse. And this is what we mean by crosstalk. So there is some unwanted interaction on this chip that makes the error rates worse. So in fact, on IBM systems, our measurements found that crosstalk can actually worsen the gate error rates by up to 10x. And this can significantly impact a program's overall reliability. So why does this kind of interference occur? This is because of some fundamental hardware reasons. For example, to enable 2-qubit gates, to implement 2-qubit gates, IBM uses coupled hardware resonators between 2 qubits to mediate interactions between them. So the 2-qubit gates shown here by the links actually correspond to a hardware resonator. Like each of the 2-qubit gates shown here corresponds to one hardware resonator. So crosstalk occurs because of overlaps in the resonant frequencies of these different qubits and because of unwanted couplings through these hardware resonators, which are very difficult to eliminate. But this is not limited to IBM systems. Crosstalk is a major source of noise in quantum computers, and it occurs in systems from other vendors also. Now, because of the importance of crosstalk, there have been several hardware efforts to reduce crosstalk. So this includes techniques like carefully selecting the frequencies of qubits to avoid collisions, restricting the connectivity of the chip to reduce the number of couplings, and this also allows us to pick a smaller number of frequencies. There have been efforts to redesign gates, and also there have been very conservative hardware scheduling policies where all nearby parallel operations are blocked. But in spite of all these efforts, we see that state-of-the-art systems still have substantial crosstalk. So the main question that our paper tries to address is what can we do about crosstalk noise in software? So although there are several research works which attempt to characterize crosstalk, here we give an example of one of them. There is really no prior work which attempts to reduce the effects of crosstalk for programs. But in fact, current compilers actually do quite the opposite. So in order to reduce the effects of decoherence, which I'll explain in a few slides, compilers actually try to maximize parallelism. So they schedule as many instructions as possible in parallel. So this actually increases the crosstalk that programs experience. So our work proposes the first software system for mitigating crosstalk. We have two main components. In the first component, we characterize the crosstalk present in a given quantum device. And in the second component, we take the intermediate representation of a program along with this characterization data, and we can schedule the program to avoid the effects of crosstalk. So we perform characterization using a method called simultaneous randomized benchmarking. And this is a standard method, but we propose several optimizations to reduce the characterization overhead by about 2 orders of magnitude. To schedule instructions, we develop a scheduler based on SMT optimization. And essentially, the optimization serializes instructions by considering the effects of both crosstalk and decoherence noise. So we evaluate these techniques on 3 20-qubit IBM systems. We do real executions on these systems. And we show that our scheduler outperforms the current best techniques by about 5.6x. And 5.6x in reliability or fidelity. And we show that our scheduler actually obtains a near optimal crosstalk mitigation in practice. So now I'll first describe our crosstalk characterization methods. So to characterize crosstalk, we first need a method to measure the gate error rates. So there is a standard way to do this. It is called randomized benchmarking. So the idea behind RB is that if I want to measure the error rate of a 2-qubit gate, I can create multiple random circuits where this gate is invoked, along with other random single-qubit gates. And we can execute a lot of these circuits on the real device, measure the data, and fit the data to a theoretical model, and estimate the gate error rate. RB is a standard technique. It is used in IBM's, Google's, and Rigetti systems. So to measure crosstalk, we first use standard RB to measure the independent error rates of each gate. So EG1 is the error rate of this gate when there's no other operation executed in parallel with this gate. Next, we perform simultaneous randomized benchmarking. So basically, we execute RB on both gates simultaneously. So this allows us to measure the error rate for G1 in the presence of G2. And this gives us this conditional error rate that we denote as EG1, Q1, G2. That is, what is the error rate of G1 when G2 is also executing in parallel. So we say that there is crosstalk between these two gates, G1 and G2, if their conditional error rates are actually much higher than the isolated error rates. Now, we performed all pairs crosstalk measurements on 3 IBM systems. These are called Poughkeepsie, Böblingen, and Johannesburg. And the figure here illustrates the high crosstalk pairs that we found on the Poughkeepsie system, but you can find the data for the other 2 systems in the paper. So from measurements on these 3 systems, we make a few observations. We see that, first we see that crosstalk can worsen gate error rates by up to 11x. So this means that if I have a gate with fidelity of about 99%, when there is crosstalk, the fidelity can reduce to about 90%, which is a serious impact for a program. We see that high crosstalk really occurs only at 1 hop distance from a gate. For example, the gate 1112 has high crosstalk with 510, but not with 05 or with 12. We also ran these tests daily for 1 week, and we saw that the conditional error rates actually vary by about 2x. And interestingly, the set of high crosstalk pairs did not really change all that much. Finally, gathering all this data is very time consuming. So on this system, it takes about 8 hours for a full crosstalk characterization experiment. And I want to stress that this is 8 hours of quantum machine time when the system is not available for any useful compute workload. So first, we want to reduce this overhead. So our first optimization is quite simple. Since high crosstalk occurs only at small distances, we only characterize gates that are separated by 1 hop distance on this chip. So this allows us to reduce the number of experiments by about 5x. And we also confirmed with the device engineers that this is the expected crosstalk behavior from the system. Next, we can parallelize experiments for gate pairs which are sufficiently separated. For example, here I can run characterization for the orange pairs, for the black pairs, and for the green pairs all together. And this can give us a further 2x reduction in the number of experiments. And in the paper, we develop an efficient bin packing heuristic that helps us find such partitionings. And finally, since the set of high crosstalk pairs was stable across days, we see that it is sufficient to characterize only the set of high crosstalk pairs every day, and periodically, say once in a week, we can run a full one-hop characterization or a full system characterization of crosstalk. So put together, this allows us to reduce characterization time from about 8 hours to under 15 minutes for these systems. So this allows us to quickly measure crosstalk and provide accurate data to our scheduling module. So let's talk about the instruction scheduling now. So consider an example 6-qubit system shown here with high crosstalk on the gate between qubit 0 and 1 and the gate between qubit 2 and 3. And let's consider a case where qubit 2 has low coherence time. So what does this mean? So decoherence is a well-known source of error in quantum systems. What this means is that if I initialize the qubit to a particular state, the reliability of the state actually decays exponentially as time passes by. So there is actually a short window of time to perform gates on a qubit, and the size of this window actually differs for different qubits. So when we execute the program on the right, as it is, using current compilers, this program incurs high crosstalk because the two gates run in parallel. So we can avoid this crosstalk if we serialize these two instructions by inserting a barrier. But if we naively serialize the instructions, then qubit 2 has a long wait time because of the serialization, and this can worsen the decoherence errors on this qubit. So what we really want is an intelligent serialization like this, which minimizes both the effects of crosstalk and decoherence. So to do this automatically, we use a formal optimization to compute the best schedule. So we develop a scheduler using a technique called SMT optimization. Our optimizer considers program dependencies, it considers crosstalk data that we collect, and it considers device calibration data to find a schedule that minimizes the impact of both crosstalk and decoherence. So let me show you how we model these executions using SMT constraints. So first, to model an execution, for each gate, we have a variable that denotes the gate start times and gate durations. We can get these gate durations using a device's calibration data. So as a basic constraint, if two gates depend on each other, then the dependency must be captured by the schedule. So if gate J depends on gate I, then J should start only after I finishes. Now, once we have this basic dependency, our schedules are same, so we can model crosstalk using this. So to model crosstalk, we want to create some kind of connection between the gate error rates and the different gate overlap scenarios in the schedule. So to do this, we basically track the overlaps between gates. So for every pair of gates that can potentially overlap, we create an overlap indicator variable, which is 1 if the gates overlap and 0 otherwise. So now let's go back to our example. So here, the gate G2 can potentially overlap with G1 or G3. It can also overlap with G0, but for simplicity, let's ignore it for now. Our implementation actually considers these kind of overlaps as well. So we have two overlap indicators, O12 and O23, to capture overlaps between G1 and G2 and between G2 and G3. And there are basically 4 cases. That is, G2 overlaps with neither G1 or G3. It overlaps with one of them, or it overlaps with both of them. So the first constraint here says that if G2 overlaps with neither G1 nor G3, then the error rate is simply the isolated error rate for this gate. If it overlaps with G1 but not G3, the second constraint says that the error rate should be set as the conditional error rate of G2 given G1, which is what we measured using our crosstalk characterization step. And if it overlaps with both, we simply model the error using the max of both the conditional error rates. And in practice, we found that this works well. So we can generalize this for an arbitrary schedule, and you can find details about that in the paper. So now that we've modeled the crosstalk errors in our schedule, now we need to model the decoherence errors. So to do this, we basically track the amount of compute time that we use on each qubit. We call this the lifetime. So we just take the difference between the finish time of the last gate on a qubit and the start time of the first gate. Once we have these lifetime variables, the error from decoherence can be approximated as an exponential loss on this lifetime. The lifetime is divided by the coherence time for this. And we can get the coherence time from the calibration data. So this way of measuring the decoherence errors is standard and well known in the literature. So given these crosstalk and decoherence terms, the overall objective of the optimization is to minimize the product of both of these terms. And the optimization does this by changing the gate schedule. So in effect, what the optimization does is it can serialize instructions whenever the gain of avoiding crosstalk is higher than the increase in decoherence errors that happens because of increasing the lifetimes from serialization. So to implement this optimization, we wrote a new transpiler pass in Qiskit that is actually open source now. And we use Microsoft's Z3 SMT solver to implement the optimization. So the output of the optimization is basically a set of gate start times. And based on these start times, we can insert the appropriate barriers necessary to enforce the schedule. So now let's move on to the evaluation. So we use three kinds of circuits: swap circuits, QAOA, and hidden shift. Here I'll show you the results for the swap circuits, and you can find more results for the other benchmarks in the paper. So swaps are a fundamental communication primitive in superconducting systems, and circuits like the one shown here are actually part of most quantum programs after they've been mapped onto the hardware. They're typically inserted automatically by the compiler. And to evaluate these kind of circuits, because they have high parallelism and they're very susceptible to crosstalk, we created 46 such circuits on regions of 3 20-qubit IBM devices that are actually affected by crosstalk. So we make these circuits generate a known quantum state. This is called the Bell state. And we can measure the error rate by generating the state and measuring the quality of the state using a technique called tomography. So in this figure, we compare the error rate for our scheduler, which we call xtalk shed, with two baselines. So the first baseline is called series shed. This baseline basically serializes all instructions in the program, and it is equivalent to inserting a barrier after every single instruction. The second baseline is called par shed, which maximizes parallelism, and this is the policy used in current compilers like Qiskit. So on the x-axis, we have different qubit pairs. For each of these qubit pairs, there is a corresponding swap circuit. And for each of the three algorithms, we use the algorithm to schedule the swap circuit, and we measure the error rate on the actual device. And we do 8,000 runs on the actual device to get the error rate. And the way to read this figure is that lower error rates are better. So across the different qubit pairs, we can see that xtalk shed obtains up to 5.6x reduction in the error rate compared to these baselines. On average, we get about 2x improvement. And I want to stress that a 5x improvement in the error rate is actually very significant, and it means the difference between a failed execution and a successful execution, especially with the current error rates in NISQ systems. So we also get similar improvements on other machines and other benchmarks. And we show in the paper that the mitigation that our algorithm provides is also near optimal in practice. Now, most importantly, since swaps are the fundamental communication primitive in superconducting systems, the improvements that we get are very significant, and crosstalk adaptive scheduling will be very crucial for reliable executions on these systems, especially as these systems scale up. So how much does this impact execution time? We found that on average, the impact is very low. Program durations increase by about 1.16x, and in the worst case, they increase by about 1.6x compared to the parallel scheduler. So this is a small increase that we need to pay for in terms of execution duration, but for NISQ systems, reliable executions are far more important than executing them quickly. So we get this large increase in reliability by about 5x, but we have to pay a small cost in terms of the duration. So to summarize, we see that crosstalk significantly affects applications. Crosstalk adaptive scheduling is very important for swap circuits and other benchmarks. And since swap circuits are so frequent in our quantum programs, ideally vendors should measure and expose crosstalk data for their devices to help us handle it in software. Our work also shows that crosstalk mitigation is not just the job of hardware. Software can offer significant advantages, and we feel that if we redesign both software and hardware together, we may actually get a better overall design point with respect to crosstalk. So to conclude, we presented the first software system for mitigating crosstalk in NISQ systems. We show using real executions that we obtain up to 5x reduction in the error rates compared to the current state-of-the-art methods. And our code is actually open source through Qiskit. Feel free to play with it. And you can also find our full paper using these links. Thank you.